In this video, we will continue the process of using software within Altair's portfolio of powerful simulation tools to assist in the design and construction of a small robotic car. Please be sure to watch our previous video and read our previous blogs about the progress on this project so far. In this portion of the project, we will focus on two important stages. The first will be implementing a speed encoder to generate some feedback signal from the drive wheels. The second will be designing and testing another subsystem to interpret that feedback as a linear speed, which will allow us to fine-tune a fully closed-loop control in the future. To begin, we will need to discuss some of the additional hardware used in this project. We will use one off-the-shelf component called an arrowhead sensor, which is a type of optocoupler. The specific part we'll be using in this project is the OPB704WZ. This sensor consists of a light-emitting diode and a photosensitive transistor. The transistor will open and close as the infrared light from the LED is either reflected back into the sensor or absorbed by the material in front of it. We can make use of this sensor by placing an encoder wheel on the drive tires of the robotic car. This encoder wheel will consist of evenly spaced sections that alternate between reflective and non-reflective. For this project, a custom encoder was created using cardstock paper with 8 sections, 4 of which are white and 4 of which are black. We will use Altair PSIM to simulate the circuit necessary to extract information from these components. There is a default optocoupler model available in PSIM that will function similarly to our real-world sensor. We can use PSIM to design and test the schematic, which will include the supply voltage, the switching frequency detected by the sensor, and the measured output across the transistor. To verify the schematic, we will assume that the maximum frequency of the encoder wheel will be 50 Hz. Using SimView, we see that the output of the sensor is roughly a square wave matching the frequency of the input, which is exactly what we need. We will now move on to combining the encoder wheel and the arrowhead sensor in the real world. We need to mount the encoder wheel directly on the tire, and we then position the sensor very close to the encoder, which will ensure reliable results. When we put the maximum voltage across the motor, we can see the output of the sensor is a rough square wave, which is what we expected. However, measuring this yields a frequency of approximately 15 Hz, which is lower than anticipated. This is not an issue though, as we now have identified the maximum speed of the robotic car. The next phase we need to complete is the design and implementation of a subsystem that can read this square wave and interpret it as a measurable frequency so that we can reliably implement a control loop. Originally, the plan for this car was to use an off-the-shelf frequency to voltage converter IC, but the input frequency was too low to accurately implement with the components we had available. Instead, we will pivot to Altair Embed, which will allow us to design and test an embedded system to accomplish this goal for us. Make sure to subscribe to this YouTube channel and routinely check our blog to stay up to date with this project and to see what else Altair has to offer. As always, if you have any comments or questions, please do not hesitate to reach out to us at trueinsight.io.